The shock wave travels at the speed of sound. 30 seconds to a couple of minutes later, depending on where in the town they were, shock wave hits the window. There were a lot of injuries from broken glass. There are also a lot of injuries afterwards, people stepping on the broken glass. About $30 million US in damage, 1,600 people were injured. Nobody died, but it was a pretty near thing. Something like the Chelyabinsk impactor happens somewhere in the world about once every 30 years. Most of the time over the middle of the ocean. Less of a problem. But we'd like to know about the next one that happens over a city before it happens. So how do we deal with this? There's a large number of survey programs that have been funded by particularly NASA for the last more than 20 years now, and also significant funding from other countries. You see here the three most prolific at the moment: the Catalina Sky Survey in Arizona, the Pan-STARRS project in Hawaii. The Wide Field Infrared Space Explorer was initially an astrophysics satellite. It's been repurposed for its extended mission solely to find and track near-Earth asteroids and characterize them. The goal here is find every possible near-Earth asteroid before it comes anywhere near the Earth, if we can. There's also a project called ATLAS, which aims to find things, most things like the Chelyabinsk impactor, with a few days to a couple of weeks of use. We still have a blind spot because we can't observe directly near the sun. There's a proposal out of the Propulsion Laboratory in Pasadena, led by Amy Mainzer, that would called NEOCAM, that would use technology derived from WISE to look right near the sun in the infrared from space, which you can't do from the ground. And that way you can find asteroids that are coming straight towards us from that direction. But the general goal here is find as many near-Earth asteroids as possible, predict their orbits out as far as we can. And currently we're discovering about 2,000 near-Earth asteroids a year. I say we. I'm not involved in these survey programs myself. There are many dozens of people involved in all of them. And I don't want to take credit for the work of other people. I do mostly characterization of asteroids that have already been discovered. So this project has gotten called Space Guard after an old Arthur C. Clarke novel, but it has done its job. Initially, the goal was to find all near-Earth asteroids larger than 1 kilometer in diameter, because something like that, no matter where it hits in the world, we're going to have a very serious problem. Fortunately, we are now tracking all of those objects. We know that we're finding almost all of them because the rate at which we discovered them went up very steeply in the 1990s as CCD cameras got better and telescope surveys started operations, and it's now dropped way steeply down almost to nothing. So we're finding and tracking almost everything that's more than 1 kilometer across in the near-Earth population. Above a few kilometers in diameter, we're tracking everything because spacecraft that are orbiting the sun can see large asteroids even on the direct opposite side of the sun from the Earth. They can't see the sort of 1 kilometer size ones. There may be a couple that are just on the far side of the sun most of the time. We'll wait for them to move around. But we can say there won't be any impacts by anything bigger than 1 kilometer across onto the Earth in the next few hundred years. There is one object that called 1950 DA that has a slight chance of hitting the Earth in the year 2880. I cannot yet rule it out. It's been annoying me for the past 10 years. Fortunately, we've got plenty of time to figure that one out. We are now extending the survey program down to find and track stuff down to everything down to about 140 meters. Maybe we can push it down to 100 meters. For stuff like Chelyabinsk size, you don't get decades worth of advance notice. You may get a few days or a week. Enough to know everybody's in the affected zone to stay away from the window. When we find the asteroids, we want to characterize them as best we can and track them as precisely as we can. This is stuff that I'm working on, particularly with groups of people at the Arecibo Observatory in Puerto Rico. You see it in the upper right. And then the Goldstone site in Southern California, which is part of NASA's Deep Space Network and run by a group at JPL for the radar program. In this case, we send out a radar signal, we code it in time, so we can image the asteroid we're bouncing the radar beam off of, and this gives us pictures like you see here. They're not as detailed as the spacecraft images, but we can study a lot more objects. And you see here just a wide range of shapes. Some are lumpy spheroids. They're not entirely round, but then you've got rocks scattered everywhere. You've got things like Itokawa, two pieces sitting on each other. This one here, 1994 CC, is kind of fun. It may not be entirely obvious. there's a bright dot there and there, above and below the asteroid itself. That's 2 small satellites. This is a triple asteroid system. It has 2 moons orbiting it, not just 1. So we're doing cool science here in addition to making sure they aren't going to hit the Earth. We do tend to get a fair number of false alarms, because initially we can't predict the asteroid's orbit all that well.